Okay, so thank you everyone for joining today. Today we have invited Dr. Anshu Gupta from the University of New South Wales, Sydney. And yeah, it's a pleasure to have her here today to talk about her recent work. So she has been awarded her PhD at the Australian National University and currently doing a postdoc at UNSW. And she will soon be joining Curtin University as an Astro 3D Fellow. And she's been working on understanding how galaxies form and evolve, and today she'll be telling us her latest work. So please, Anshu, take it away.
Thank you, Rayu, and thank you very much for inviting me to give this talk. I know it would have been better to give this talk in person, but at least we can do this. Our work allows us to do is meet virtually and talk virtually. So that's great. So yeah, as Rayo said, that I will be talking about how galaxies form and evolve. And in my work, I've used both observations and simulation. Yeah. Sorry, I'm just rearranging the Zoom window. All right, I think this should work for me now. Yeah, so if you have attended any galaxy evolution talk, then you must have seen this plot. This figure here shows the cosmic star formation rate density and how that cosmic star formation rate density evolves with redshift. And it shows that cosmic star formation rate density took about 3 gigayears to reach at its peak at about redshift of 2. This epoch we call cosmic noon. And after this redshift of 2, the cosmic star formation rate density fell monotonically over the last 10 gigayears, roughly. So this decline in cosmic star formation rate density, it happens for various reasons. For example, galaxies, they run out of fuel, they are very far apart, so the gas is really dense, so it can't really cool down and continue future episodes of star formation. But one of the other factor is the emergence of large-scale structures. We have known, we know that in the local universe, very few galaxies which live in the cluster environment, they are actively forming stars. So this figure here shows the average star formation rate density as a function of distance from the center of the cluster. So this region here roughly corresponds to about field universe. The density is really low. And the left-hand side of this plot is the centers of the galaxy clusters where the density is really high. And you can see that there is this gradual linear decline in the average star formation rates of the galaxy as we go from these outskirts of the galaxy clusters to the center. Basically, there's very little star formation happening in the center. The environment not just affects the star formation, it also affects how galaxies look like. So for example, in cluster environments, or especially in the centers of the clusters, almost all galaxies, they look like these red spheroidal elliptical types. Whereas in the field galaxies, more field environments or low density environment, most galaxies have this nice spiral pattern, or they have a disky stellar distribution. Basically, we think that in cluster environments, tidal interactions or galaxy-galaxy harassments, they kind of distort and destroy the galactic disk and turn spiral and disky galaxies into spheroidals, etc. But we know that, so in the past 2 slides, I've shown that environment, it drastically reduces how fast galaxies are forming stars. So the question is, does environment also affects how efficiently galaxies are producing metals? Does it affects the rate of production of metals in this galaxy? And why do we think that it could be a difference of metal production? Because most metals, as far as we know, they are produced in the stars. And since star formation rate is affected in the dense environment, so maybe there is an effect on the metallicities of the galaxy itself. So to see if environment affect the chemical evolution of galaxies, what we do is we try to look at where the cluster galaxies lie on the mass metallicity relation. Basically, the left plot here is, or the only plot on this slide, is the mass metallicity relation. And we have known about these relations for a while now. It's about 15 years, 16 actually. The mass metallicity relation, it shows that the gas phase metallicities of the galaxy rises monotonically as we go towards higher stellar masses. The relation is more like a linear power law kind of relation at the low mass end, and it saturates at the high mass end. And to understand if environment plays a role on the chemical evolution, we look at if the cluster galaxies lie above this mass metallicity relation or are they below this mass metallicity relation. And this is exactly what is shown on this plot. This is the one study which was done about a decade ago. It uses data from the SDSS survey. So SDSS survey is a survey in the local universe, and all galaxies are roughly 0.01 redshift. And it divides all the SDSS galaxies into cluster and field sample. The cluster galaxies are shown by the open circle, and the field galaxies are shown by the solid circle. And it compares if the gas phase metallicities are different in the two environments. And I won't blame you if you say the answer is no on this plot, because there's hardly any difference, especially at the high mass end. But we do see some enhancement in the metallicity, that low mass cluster galaxies are slightly more metal rich than the field galaxy at the low mass end. But at the high mass end, there's absolutely nothing. The problem with these local studies is in the local universe, hardly any cluster galaxies are forming stars. I showed you in the couple of slides back that most galaxies which are in cluster environments at redshift 0, they are not forming stars. To measure gas phase metallicity, we need galaxies to be actively forming stars, because that's how we measure gas phase metallicity. So this sample at redshift of 0, they are biased towards a couple of galaxies which are star forming, and most of those galaxies are going to reside in the outer galactic region. So we are not really probing galaxies which are in the centers of the clusters and are going to be most affected by the environment, the local environment in which they live. So this problem that galaxies are not really forming stars in the local universe, it can be resolved if we move to slightly higher redshift, around intermediate redshift. And this is one study that we did at around where we tried to target two clusters at redshift of 0.35. And there we looked at gas phase metallicity, and we found a significant increase in the gas phase metallicities of the cluster galaxy. The contours are the field environment, and you can see that all of our sample, which are these diamonds, they lie above these contours. That is, almost all cluster galaxies, they have significantly higher metallicities than the field environment. In fact, we also found a nice correlation that galaxies which lived closer towards the cluster center, they were slightly more metal rich than the galaxies which are in the outskirts. However, our samples are a bit small in this in this study, so we can't derive any conclusive conclusions about it. So essentially, in the mass metallicity relation, what we find is cluster galaxies at redshift of 0.35, they have nearly 0.2x higher metal content than field galaxy. And MAGPIE survey, which is an ongoing survey, they are going to target exactly this intermediate redshift regime, and they are going to have a range of environments to really target this whether environment affects the chemical evolution, and it will be great in the next few years when we have all the data. But for now, just with the slit data that we had in our work, it becomes a bit difficult to really distinguish whether the enhancement on the mass metallicity relation we are observing is real or whether it's an observational effect. So for example, what happens when the what could happen when galaxies fall into the cluster environment? They experience this stripping, ram pressure stripping. Basically, the intracluster medium of the cluster environment, it puts a pressure on the intrastellar medium, or ISM, of the infalling galaxy, and it removes the outer parts of this galaxy. So basically, the galaxies, as they fall deeper and deeper into the cluster potential, their outer galactic disk, or the gas in the outer galactic disk, gets stripped off. So if we are doing an integrated measurements of these galaxies, then we can observe an artificial enhancement in the metallicities of the galaxy because our measurements are biased towards this central, more metal rich part of the galaxy. So to estimate if this observational effect could explain these observations of 0.2x higher metal content, we try to use some analytical model and mock observation technique. So what we did was we developed an analytical model of ram pressure stripping. So this model is basically balancing the pressure imposed by the ICM or intracluster medium onto the infalling galaxy to the gravitational potential that is holding on to the gas which is in the galaxy. And after making a few assumptions, we can reach to a very nice analytical solution. And there are only few free parameters, or in fact, two free parameters in this model. One is how far this galaxy is from the center R, how far this galaxy is from the center of the cluster, and how fast this galaxy is falling into the cluster potential. All the other parameters you can get directly from observations. So for example, stellar disk scale length and central surface densities, these you can get directly from photometry. And the ICM density profile, they are also can be estimated from X-ray observation and some weak lensing mass measurements. So yeah, now we have this really nice model of how ram pressure stripping works. What we do is we apply this model onto a bunch of CALIFA galaxy and sort of artificially strip them. What we do is we select one CALIFA galaxy, assume some parameters, the two independent parameters, distance and infall velocity, calculate the stripping radius, and truncate, remove all the galaxy which is outside this stripping radius. Right. Now, then we redshift this galaxy to the redshift of our observation and do mock observation to directly match with what we had in our previous data. So we are trying to conduct mock observation and try to match as best as possible with our observations. Do we get similar results? Do we see an enhancement in the metallicity? Not really. So the left-hand side plots are the direct observations that we get, where our observed cluster galaxies were significantly above the mass metallicity relation. The right-hand side plot is for our mock observations, which are these ram pressure stripped galaxies. And you can see that their mass metallicity relations are identical to what you will get from for the field sample. Basically, this removal of the outer galactic disk cannot produce a significant enhancement or cannot significantly alter the gas phase metallicities of the galaxies that we are observing. So this 0.2 dex increase in the metallicity that we got for our data, it's actually real. So there is some, at intermediate redshift, there is an enhancement in the metallicities of the galaxies which live in dense environment. Then the follow-up question is, what are the other physical mechanisms? What are the physical mechanisms that could be responsible for this? And over the years, many physical mechanisms have been proposed. For example, strangulation. The galaxies are forming metals without having inflows of pristine gas in the cluster environment, and that can boost up their metallicities. Or enriched accretion, basically in cluster environments, galaxies are accreting metal-rich gas. But observationally testing these different scenarios, it's a bit tricky. However, over the last decade, what we have achieved is we have developed really decent cosmological simulations. Advantage with this cosmological simulation is, in this simulation, galaxies and their environment is simulated simultaneously. So we can start to figure out, or we can start to ask question, how environment is playing a role. Does environment affect the evolution of galaxy? When does it affect it, and how? But remember, with all these simulations, we have to remember that any predictions or any measurements that we are measuring, there is a caveat, which is it could be dependent on the underlying galaxy evolution models that you have inbuilt in the simulations. But still, these cosmological simulations, they are a great avenue to test out what's happening what could be happening to the galaxy. So we tried to do this in simulation, try to use illustrious simulation to see how galaxies in dense environment enrich themselves, and do we see a sign of metallicity enhancement. So to do this, what we do is we select all galaxies which are living in cluster environments in present day universe, for example redshift of 0. We track them back in time and identify at what redshift they fall into the cluster environment. So for example, at really high redshift, all of them are in falling. That is, at a high redshift, none of them have really fallen into the cluster potential. But as we go to lower and lower redshift, more and more galaxies, they are becoming these red circles, which are already in the cluster potential. So once we have separated galaxies into these two categories, infalling and accreted. Infalling galaxies are the ones which are outside the cluster potential. They haven't yet experienced any environmental effects, supposedly. And accreted galaxies are the ones which are within the cluster potential, and there we should expect to see environmental effects if they exist. So we have these two samples. Now we can start to ask, do we see that galaxies in the dense environment, they evolve differently in terms of their chemical evolution? For comparison, we also select a sample of galaxies which live in the low mass halos and track them back in time, and they will serve as a comparison field sample. So what's the mass metallicity relation of these three samples look like at redshift of 2? So at redshift of 2, all the three samples, the accreted galaxies, galaxies which live in the dense cluster potential, infalling galaxies which are outside the cluster potentials but will be at a later stage, and the failed galaxy, all of them, they have similar mass metallicity relation. That is, at redshift of 2, there is not really any effect of environment on the mass metallicity relation. We used observations. Last year, we published a paper with Leo Elcon. She's a PhD student at she's a York, not a PhD student now. She was a PhD student. Now she's a York fellow in Canada. So this paper came out last year, and we used two clusters, Cosmos and UDS cluster. Both of them, UDS is at redshift of 1.6 and Cosmos is at redshift of 2. We measured mass metallicity relation for these two clusters and found no effect of environment in these two clusters directly. So basically similar to what we saw in lustrous, right? What happens when we go to lower redshift in lustrous? So this plot now goes to lower redshift and just focus on how the mass metallicity relation of accreted galaxies which live in the cluster environment, changes with respect to the failed galaxy, the blue triangles. Basically, below redshift of 1.5, we see a consistent increase of about 0.08 to 1 dex in the metal content of cluster galaxies compared to the field, irrespective of the stellar mass. The difference changes slightly, but overall we see that the environment really matters, at least in this TNG 100 universe. In fact, we have another sample, which is these infalling galaxies, right? In fact, these infalling galaxies, they also showed some higher chemical abundance. Lower redshift, we saw the effect only at redshift of 0.5, and it first appeared in the low mass galaxies, but then at redshift of 0.2, it's consistent across. So even these infalling galaxies, the galaxies which have yet to experience the dense cluster potential, they have about 0.05 dex higher chemical abundance than the failed galaxies, than the galaxies which live in low mass halos. So that's interesting. So basically what we have shown that environment matters in terms of chemical evolution, and it kind of shows up around redshift of 1.5. But you can go a step further in simulation and you can start to ask, how does environment matter? What has the environment changed? And this is what we did. And one thing that we tried to test out is, does the metallicity of the gas these galaxies are accreting, is that different? So in this plot here, I am showing the metallicity of the gas, of the inflowing gas as a function of redshift. So this is the gas which is falling into the galaxy, and it's going to be responsible for the next generation of star formation. So at redshift of 2, the metallicity of inflowing gas is really, really low. And it's almost similar for both the field and the accreted galaxy sample. But as we go to lower redshift, this metallicity of inflowing gas increases. That is, this inflowing gas, it becomes a bit less pristine. It has more metals. But In the cluster sample, the metallicity of inflowing gas is about 3 to 5 times more than the metallicity of inflowing gas in the field. That is, the galaxies which live in the cluster potential, they are accreting significantly metal-rich gas than the galaxies which live in the field environment. In fact, even for these infalling galaxies, the galaxies which are outside the cluster potential, even they are accreting more metal-rich gas than the field galaxy. So we suspect that this accretion of enriched gas, both in the infalling and the accreted cluster galaxy, it's driving the higher chemical abundance. We think that the inflowing gas could get mixed up with the intracluster medium, and this intracluster medium has been shown that it develops roughly around redshift of 1.5 to 2, and this could be responsible for enriching the metallicity of inflowing gas, but that still needs to be investigated further. So just to summarize this first part, what we have found is found is that we find a significant increase in the chemical content of star-forming galaxies, at least at the intermediate redshift of 0.35, and this increase in the metallicity of cluster galaxies, it's not an observational effect. It's not because the galaxies are stripped off from the outside and our measurements are only biased towards the central, more metal-rich part of the galaxy. And from simulations, TNG100 simulations, we find a significant effect of pre-enriched gas accretion on the chemical evolution of galaxy. We find that accreted cluster and infalling galaxies, they are significantly more metal rich than the field galaxy, and they are accreting metal rich gas than the field galaxies. So just to change gears, in the second half of of this talk, what I'll be talking about is the mass assembly history of the galaxies, how galaxies they assemble their mass. So right now we know that galaxies, they undergo this two-phased mass assembly. One, the initial collapse, basically the gas cloud initially collapse, and most of the stars that the galaxies is going to have, they are going to come from in situ star formation. I'm not saying that the galaxy in this process is not accreting gas. It's just that most of the things that are coming in, they are gas clouds, and most of the stars the galaxy is going to have, it's going to come from in situ star formation. And after a while, the growth of stellar mass through the hierarchical merger, that kind of dominates. Basically, the galaxies merge with other galaxy, and that's how their stellar mass increases. But we still don't know when does this transition happen. We still don't know when does the galaxies transition from this in situ stellar mass growth to an in situ stellar mass growth. To understand how galaxies assemble their mass, the kinematics of the gas and the stars has been used for a while now to understand how galaxies assemble their mass. And this is one of the first observations, which is it shows the rotation curves of Andromeda galaxies in going really far out, and it shows that it gave one of the first indications of this gravitationally only interacting dark matter component of the galaxy, and it showed that this dark matter component is dominant matter component in the outer galactic disk. And this kinematic and information, how fast and how fast gas is rotating, can really tell us about the overall matter content or overall mass content in galaxies. And we can use this kinematics to get a handle on when the galaxies transition from the monolithic collapse to the hierarchical merger. So to understand this, what we are doing is we are targeting galaxies which are between redshift of 3 to 4. This redshift 3 to 4 is really important epoch in the cosmic star formation rate density, because in our universe's history, because this is just before the peak in the cosmic star formation rate density. It's just before cosmic noon. And by looking at how galaxies transition from between redshift 3 to 2, we can understand what led to this peak in the star formation rate density and its subsequent decline. And its subsequent decline. So what we are doing is we are using this MOSEL survey, which is multi-object spectroscopic emission line survey. It's a census of emission line galaxies between redshift 3 to 4, and we are using both Keck and VLT for this survey. Sorry. Yeah, so the figure here shows the redshift distribution of our initial sample, and it shows that we are going really deep in the K band. Some of our galaxies, they have K band magnitude of about 24.9 9 or so. So the survey is really deep. And this is one of the spectrum from our survey. K band, it shows the red stream O3 line, right? O3 line, 5007, O3 4959, and H beta emission line really clearly. Sorry, I like this spectrum. Yeah, so the topic of this talk will be the width of this emission line, and what we are going to be focusing on, the information contained in the width of this emission line, because the width of this emission line, it represents a combination of overall rotation the gas has and the intrinsic velocity dispersion of the gas. Since it's really hard to get resolved kinematics of the galaxies at redshift of 3, so the only thing that is currently accessible to us are these integrated velocity dispersion measurements. And hopefully with JWST, this thing can improve and we can get some resolved kinematics. But till then, we rely on the integrated velocity dispersion or integrated measurements. So we estimate this integrated velocity dispersion, which is this width of this O35007 emission line for all of our MOSEL galaxy, and compare how this integrated velocity dispersion looks like with respect to the other sample. Why we are focusing on this integrated velocity dispersion? Because these two components, they are really important. The overall rotation velocity, it can tell us about the total gravitational mass within the galaxy, and the intrinsic velocity dispersion gives us a handle on total amount of turbulent energy in the gas. So these are our measurements on this plot. So what we are plotting is how integrated velocity dispersion on y-axis and the stellar mass of galaxies on x-axis. Our sample is given by these stars, golden stars, and on this plot we are comparing our measurements to other samples at redshift of 2. So there are two things on this plot that are they are good to notice. One is at the low mass end, our redshift 3 galaxies, they have same integrated velocity dispersion as other samples at redshift of 2. But at the high mass end, our integrated velocity dispersions are significantly lower than the same stellar mass galaxies at redshift of 2. So we are measuring the integrated velocity dispersion and the stellar mass for all of the samples on this plot. They are measured in the same way. So we do not suspect that these samples will have significant systematic effect differences between them. But there can be still biases in how the samples were selected. But with keeping aside those biases, what we are finding is that at redshift of 3, massive galaxies, they have significantly lower integrated velocity dispersion than the same stellar mass galaxies at redshift of 2. How does our measurements compare with redshift 3 samples, existing redshift 3 samples? Sadly, there are not that many samples at redshift of 3 because it's hard to measure them. We find one study which has provided these integrated velocity measurements, but they don't have any high mass galaxies in their sample. Their low mass sample matches pretty well to what we have, so that's reassuring. So essentially in this plot, what we are finding is massive galaxies at redshift 3, they have about 50 kilometers lower integrated velocity dispersion compared to the same stellar mass galaxies at redshift of 2. So that's interesting. And the question is why? What could be the possible reason? And as I said earlier, the integrated velocity dispersion, it represents a combination of overall rotation of gas and its intrinsic velocity dispersion. Basically these two quantities, total gravitational mass and gas turbulent energy. So what is different between redshift 3 and redshift 2 galaxy? In terms of gas turbulent motion or intrinsic velocity dispersion, we know that intrinsic velocity dispersion from KMOS 3D surveys, for example, that intrinsic velocity dispersion, it rises monotonically as we go from redshift 0 to high redshift, like redshift of 2 or 3. So maybe it's the intrinsic velocity dispersion, it does not change that much between redshift 2 to 3. However, these measurements at redshift of 3, they are extremely limited. We only have about 5 galaxies at redshift of 3 with resolved kinematic. So we can't really rely on them beyond redshift 2 beyond redshift 2. So maybe not. It's the intrinsic velocity dispersion that's changing. Another thing that could be different is this total gravitational mass. For that, we really need resolved kinematic measurements to really disentangle this rotation and velocity dispersion. And with the current instruments, we cannot do that. We don't have the spatial resolution to do that, to get resolved kinematics. But hopefully with the James Webb, we might be able to get some samples with the resolved kinematics at redshifts greater than 3. And that will help us disentangle this mystery. But another thing that we can go to is look at observation, go to simulation and see what's changing in simulations for massive galaxies when we go from redshift 2 to 3. And one thing that we found that is changing is how much galaxies are, how much of the stellar mass the galaxies have is coming from XC2 processes. So the XC2 stellar mass fraction, which is plotted on the y-axis here, is basically the amount of stellar mass galaxies have that is coming from other galaxies. For example, it could come from mergers, minor mergers, major mergers, or even mini mergers, whatever. But all of these stars, they were assembled into other galaxies and later on were accreted into our main galaxy. So this XC2 stellar mass fraction, it remains, for the low mass galaxies, it remains almost flat. Like that is between redshift 6 and 1, it does not change at all. But for massive galaxies, we see that this XC2 stellar mass fraction, it increases beyond redshift of 4. That is, we see a systematic increase in this XC2 stellar mass fraction going from redshift 4 to 2. And we think that this transition in how galaxies build up their stellar mass, transition from stellar mass buildup via in situ processes to XC2 processes such as mergers, that could be responsible for raising the integrated velocity dispersion that we had in our observations, as we had observed. So to conclude this analysis, what we are finding is that beyond redshift of 2, massive galaxies, they assemble their stellar mass through XC2 processes, and this growth via XC2 processes might be driving the higher integrated velocity dispersion at redshift of 2, as we had observed. Another thing that we found interesting in this paper when we looked at simulation is how the stellar sizes of the galaxies evolved. So on this plot here, I'm showing the stellar disk sizes of the galaxy as a function of their stellar mass. Just focus on the shaded region, which are taken from the simulations. So pink is redshift 3, and the black triangles are for redshift 2 sample. So you can see a dramatic increase in the sizes of the stellar sizes of galaxy as we go from redshift 3 to 2. At the low mass end, stellar sizes between redshift 3 and 2, they are pretty much the same. But at the massive end, we see a significant increase in both the scatter and the mean. So that was interesting. And to try to see what led to this rise in the sizes of the galaxy, we tried to identify some galaxies which had developed this really large stellar sizes. So this plot here is essentially the previous plot, but now I'm showing the galaxy selection. So what we do is we select 2 populations of galaxies which are extended and normal size. So extended galaxies are the ones which have whose stellar sizes is about 1 sigma above the size-mass relation. For comparison, we select a sample of normal galaxies whose sizes are within 1 sigma of the size-mass relation. And also to account for the changes in the stellar mass or the star formation rates between the two samples, we match these two distributions to the T. Basically, at redshift of 2, the stellar mass and the star formation rate distributions of these two populations are exactly the same. So any differences in the two populations has to be driven by something else. Right. So now we have selected our galaxies at redshift of 2, extended and normal size. What we can do is track these galaxies back in time and see how the sizes and the stellar mass of these galaxies evolved differently and when did it evolve differently. And this is exactly what is shown on this plot. It is again the size-mass relation, but now I'm plotting how the sizes of galaxies evolve from high redshift to low redshift. So essentially, on the left hand side of this panel is the same normal galaxies at higher redshift and going to high redshift, which is redshift of 6, going to the redshift of 1. So the bottom panels are give the same measurements, but now the median for the entire population. So this is what the median of normal mass size massive galaxies look like at redshift of 6. And this would be the median of size mass for the normal massive galaxies at redshift of 1. So what this plot shows is that extended massive galaxies, as they are evolving on this size mass plane, their sizes are increasing. As they are building their stellar mass, their stellar sizes are increasing monotonically, right? But for the normal massive galaxies, as they are building or as they are growing in their stellar mass, their stellar sizes are hardly changing, at least between redshift of 2 to 4. There is absolutely no difference in the stellar sizes of this normal size massive galaxy going from redshift 4 to 2. They do experience an increase in their stellar sizes below redshift of 2, and that could be driven by these normal size massive galaxies experiencing some dry mergers that can increase, sort of fluffs them up. But between redshift of 2 to 4, the normal size massive galaxies, they are growing centrally, whereas the extended massive galaxy, they are growing outward. They are building their stellar disk. They are bulking. They are bulking up, but they are puffing as well. So basically, what you can say is extended massive galaxies, they grow outward between redshift 2 to 4, whereas normal size massive galaxies, they are only growing inward. They are only building their central stellar density between redshift of 2 to 4. And that is why we are saying that these two populations, they lie on a very different location on size mass plane. And so why do they experience such different size mass evolution? The answer lies in their merger histories. When we looked at their merger history, the number of mergers, etc., all of them were pretty much the same. But when you look at the mean gas fraction of mergers, basically, did the galaxy, so these are the overall gas fractions of the merging component, right? So the extended massive galaxies, they have encountered relatively drier mergers. Mean gas fractions of the mergers encountered by the extended massive galaxies is lower than the mean gas fractions of the merger encountered by normal size massive galaxies. Basically, the extended massive galaxies, they encountered relatively drier mergers compared to the normal size massive galaxies. These drier mergers, they are going to bring in less gas and more stellar component. And when galaxies, they experience drier mergers where merging component has more stellar particles, those stellar particles tend to reside in outer galactic disk. And those stellar particles might be responsible for buildup of the extended stellar distribution for the extended massive galaxy. Right. But one of the most interesting thing about these two populations is what happens to them afterwards. What happens to them after redshift of 2? In particular, their star formation histories. So these three plots here, They show how the evolution in the stellar sizes of the two population and their star formation rates. So you can see that on the left, the stellar mass buildup of the two population are roughly the same between redshift 6 to 0, but their star formation histories are extremely different. You can see that as soon as these normal size massive galaxies, we select them at redshift of 2, as soon as we go beyond redshift of 2, a lot of them start quenching. We see a sharp decline in their star formation rate. Whereas for the extended massive galaxies, we see that their star formation rate continues for a while before declining continues for a while. And this effect becomes more prominent when we just try to estimate the quenched fraction. So the plots here they have the same information as the previous plot, but plotted slightly differently. So now we are calculating quenched fraction. Just focus on this number and how this quenched fraction changes for the two population as we go from redshift 2 to redshift 0.3. So at redshift of 2, both population, normal and extended massive galaxies, they almost all of them are star forming at redshift of 2. Only 6% are quenched. But as we go to redshift of 1.5, almost 40% of the normal massive galaxies have already quenched, whereas only 20% of the extended massive galaxies are quenched by redshift of 1.5. And in fact, by redshift of 1, this difference increases even more. By redshift of 1, 70% of the normal massive galaxies are quenched, and only 35 or 36% of the extended massive galaxies are quenched by redshift of 1. Whereas by redshift of 0.3, almost all, irrespective of normal or extended, almost all of them are quenched, and the distribution, specific star formation rate distributions are similar. But what we are finding is these extended massive galaxies, they quench later than the normal size massive galaxies in our simulations. The star formation quenching process, it begins later for these extended massive galaxies. Are there any observational signs of this effect? Yes, actually, there are. So this is a figure taken from one of the observational work published 2 years ago about, and it shows the equivalent width of H delta versus the 4000 angstrom big. And the relation between these two quantity can tell us about the age of the stellar population. And all the galaxies on this in this analysis are quenched galaxies at redshift of 1. And basically, galaxies which reside on the left-hand corner of this plot, they are going to have younger stellar population, whereas the galaxies on the bottom right panel, the bottom right corner, they are going to have older stellar population, right? So what they did was they divided their quenched galaxy sample into galaxies which have larger stellar disk, galaxies with larger stellar disk to smaller. And what they found was these galaxies, quenched galaxies with larger stellar disk, they had slightly younger stellar population than than their more compact counterparts. Sorry, I wanted to just mask this panel because our analysis or our illustrious sample is very similar to their low mass sample, because we are also removing all galaxies above 10 to the power 11, because TNG 100 does not have samples, significant galaxies above that stellar mass range at redshift of 2. So basically, once we mask out that high mass sample, what their observations almost align with what we are finding in simulations, that quenched galaxies with larger stellar disk, they have younger stellar populations than the quenched galaxies with more compact stellar disk. Right, that's good, which was really good. But in simulations, what we can also try to answer, why do the star formation quench later in extended galaxy? And one of the key features for star formation quenching is how AGN acts, especially in these massive galaxies, how AGN behaves. And what we find that the AGN is the extended massive galaxies, their central supermassive black holes, they have slightly lower masses and they are accreting at lower speed than the central supermassive black holes in the normal size massive galaxy. Basically, the extended massive galaxies, they have weaker black hole feedback, or if we can call that. Another main ingredient of AGN feedback in illustrious model is the kind of feedback that is active. So in illustrious, illustrious implement feedback into two modes: kinetic mode and thermal mode. In thermal mode, the gas in the neighborhood region that gets thermally heated, whereas in kinetic mode, the gas gets pushed out from the center. And lots of studies have shown that this kinetic mode is more effective at quenching star formation than just the thermal mode feedback. And in fact, what we find that in extended massive galaxies, this thermal feedback, the kinetic feedback is not as effective. In fact, in almost 50% of the extended massive galaxies, kinetic feedback has not even kicked in yet than the normal size massive galaxy. And therefore, we suspect this lack of kinetic feedback and or weaker black hole feedback might be responsible for the delayed onset of star formation quenching in, uh, in the extended massive galaxy. So just to summarize this whole discussion, that extended massive galaxies, they experience drier merger. Due to these drier mergers, they build up an extended stellar disk. Since dry mergers, they are not as effective as funneling the gas towards the galactic center. So the black hole, the growth of the central supermassive black hole in these extended massive galaxies is relatively slow, due to which the black hole feedback is weak, and the weak black hole feedback could be responsible for the delayed onset of star formation quenching in these extended massive galaxy. All right. This paper will be out on arXiv tomorrow, so if you want to have more detailed look at it, you please feel free and let me know if you have any feedback. Yeah, so just to this is summarizing this whole discussion on mass assembly histories of massive galaxies at redshift of 3. What we are finding is between redshift 2 to 3, there is a transition in how the massive galaxies are built up their stellar mass. They transition from stellar mass built up via in situ star formation to stellar mass built up via ex situ processes. And we see the effect of this transition observationally. We see that between redshift 3 to 2, there is a change in the integrated velocity dispersion of the massive galaxy. Find that at redshift of 3, massive galaxies, they have about 50 kilometers lower integrated velocity dispersion than the same stellar mass galaxies at redshift of 2. Another thing that we find this interesting population of massive galaxies which have really extended stellar disk, and these massive galaxies with the extended stellar disk, they are going to experience the star formation in these extended massive galaxies. It quenches later, and we think that it's the weak supermassive black hole feedback that's responsible for the delayed onset of star formation quenching. Right. In the next couple of minutes, I just want to spend few slides on the projects that I will be doing when I move to Curtin University. So one of the things that I'll be undertaking, and it's part of the MOSEL survey, is look at epoch of reionization. So this figure here, it shows nicely how our universe transition from Big Bang to present day. So our universe, it underwent many phase transition. It was fully ionized very close to the Big Bang. It became neutral during the dark ages. And at the end of the dark ages, when the first stars and the first galaxies, they emerged, they start to reionize the universe. They start to drive these ionization bubbles into the intergalactic medium, ionizing the neutral hydrogen. And by about redshift of 6, almost the entirety of this universe, most of our universe was reionized. So this transition from the dark ages to the fully ionized universe is what we call epoch of reionization. And this understanding how this reionization progressed, which galaxies were responsible for reionization, is one of our biggest question in current astronomy. And this is what I'll try to tackle as my project when in the next few years. So there are multiple ways that you can try to understand the galaxies responsible for reionization. One direct way would be to directly observe galaxies in the reionization. But the problem with that is even with James Webb, there will be many galaxies which will be hidden underneath this thick blanket of neutral hydrogen. So it will be really difficult to directly observe the galaxies. Moreover, since the signal to noise are going to be really weak, so we won't be able to really get detailed information for these galaxies during the epoch of reionization. Alternate approach to this would be, which and it has been used been used in the last couple of years, is try to find analogs of these galaxies at redshift of 3. Am I on time?
Yeah, we have 6 minutes left to the hour.
Oh, okay. I wasn't looking at the time.
Yeah.
Sorry. Yeah, just last minute. So another approach is to look at analogs of galaxies at redshift of 3. And these analogs, and this is what I will be doing. So what we have done is we have selected extreme emission line galaxies, which are super star forming. They have really bright O3 lines. Basically, and they are sort of dwarfish. And basically, these galaxies, they have similar properties to the epoch of reionization galaxies. And so what I'll be doing is I will be targeting them with I have already gotten 3 nights of CHEMICA observations, and we have really nice O3 emission profiles for these galaxies. And in the next few years, I will try to measure how efficiently these galaxies are producing ionizing photons, and how many of those photons are escaping the neutral intergalactic medium, or could escape to the neutral intergalactic medium. So basically, what with this project, we'll try to get a handle on epoch of reionization. And with that, I'll leave you with my summary slide, and that's it. Thank you. Sorry for going a few minutes.
Thank you very much. If Anshu, an applause virtually or really. So yeah, thank you very much for the really nice overview of your kind of wide area of research. Does anyone have any questions? If you have any, please write into the chat box or raise your hand in the Zoom feature. So yeah.
I do have a question.
Oh yeah, please go ahead.
Hi Anshu, thanks for your very nice presentation. So I do have a simple question that reflects my ignorance of your field.
There are no simple questions.
So you mentioned extended versus normal stellar disk sizes. So I was just wondering, how do you measure the stellar disk size at moderate or high redshift? I assume you cannot resolve the galaxies, or are you relying on the line wave and infer velocity? How do you do it?
So the extended and normal size galaxies, they have been, that analysis is done in simulations, and that is not done observationally. And in simulations, what we do is we try to calculate the radius which encloses about 50% of the stellar particles, because these cosmological simulations, they cannot resolve individual stars. So they have so in TNG 100, for example, each stellar particle is of the mass of about 10 to the power 6. So what we try to see is what radius contains about 50% of the overall stellar mass of this galaxy. And we use that as a proxy for the stellar size.
Okay, I see. Thanks.
Yeah.
Yeah, I also had a question about your first topic.
Mm-hmm.
So you mentioned that the outer stripping of the galaxy didn't really affect your mass metallicity relation, but why is that? Is that because the outer parts are dark anyway, so it doesn't really matter?
Yeah, exactly. Exactly, because most of the light that galaxies emit, they are coming from the central part. So our measurements are inherently biased towards the central metal-rich part of the galaxy. So removing that outer low luminous region does not significantly alter overall metallicity content that you're going to measure.
Okay, and the bright parts are really hard to strip off through just.
Yeah, because they are in the center, they are deeper in the potential well, so it's really hard to strip off those central parts. Yeah. And in fact, the prescription that I used, it's actually quite drastic prescription. So it's an upper limit on how effective ram pressure stripping could be, because what we had assumed was all the galaxies that are going to be falling in, they are going to have radial orbits, whereas that's not the case. and in the real universe. So that's one extreme ramp pressure stripping scenario. So if that cannot produce significant change in the metallicity content, then I don't think ramp pressure, just the removal of outer galactic disk, it won't be enough.
Okay. Yeah. I also had another question, does anyone else have any?
I have another one,
Oh,
if there's no one else. So you briefly mentioned JWST, and you said that it could improve some of your measurements. What do you think would be the most significant improvement in your field that you'd expect from JWST? Would you be able to probe a higher redshift?
So two things, yeah, exactly. So right now with the ground-based instruments, for example, even with AO, we cannot get resolved kinematics of galaxies at redshift of 3. Especially one thing is samples becomes really limited because there are not that many massive galaxies with an adaptive optic stars at redshift of 3. Even if you find one, it's really hard to observe. It's the spatial resolution that you are going to get even with AO is not enough. But with JWST, you can get spatial resolution to get resolved kinematic. So what you will be able to do is get separate measurements for the rotation of the gas and separate measurements for the intrinsic velocity dispersion. So you can put a handle on whether how the overall gravitational potential of the galaxies are changing, or whether the gas turbulent motions that is changing with galaxies. So that is one thing. So in that JWST will really do well. Another thing that JWST will do well is make these redshift 6 to 10, 9 galaxies accessible. So right now with near infrared instruments, you cannot go beyond redshift of 3. You can go beyond redshift of 3, but you cannot detect the emission lines or the signatures that we usually use to interpret the observations. But with JWST, you can get typical O3, which is 5007 line, which we use quite regularly. You can observe that line even for like redshift 9 galaxy. So it will make that part of those redshift 9 really high redshift galaxies accessible and interpretable.
Okay, thanks. Let's not keep mentioning JWST then, or it will continue getting delayed.
Yes.
Thank you. Yeah, so I also had another question about again the first part. So your analysis showed like the cluster galaxies have more metallicity, so below about 1.5. But as far as I remember, in one of the earlier slides, the like Z equals about 1.01 galaxies didn't have any difference between the clustering field in the mass metallicity relation. But how did that suddenly change in like the local universe?
Yeah, so the thing is, it's more about how you are selecting galaxies. To observationally estimate metallicity, we need emission lines because that's how we measure metallicity, gas phase metallicities at least. And to have emission lines, galaxies needs to be actively forming stars. So and every observation has some threshold in the stellar mass, in the star formation range, beyond which it cannot detect those emission lines. So once you set a stellar mass range like that below which you cannot detect galaxy, the differences starts to become really small. So in the analysis which I presented with simulations, I was selecting galaxies, all galaxies which are star forming, essentially any galaxies which has star formation rate greater than 0. That was part of my part of that discussion. But as soon as you start to impose, for example, I can only have galaxies which have star formation rate greater than 0.5 solar per year. You start to see that the differences become really small because those metallicity enhancement signatures, they only exist in galaxies which are undergoing this suppression in star formation because of environmental effect. So you really lose out because of low signal to noise in observations in the local, especially in the local universe, because star formation in the cluster environment really goes down.
I see. Yeah, thank you very much. Does anyone have any last minute questions? If not, let's thank Anshu again.
Thank you.